Okay, so jumping into a few practice problems with related rates. Here I'm going to start with a graphical example because I feel like these are sometimes a bit confusing for folks, especially when there's no direct formulas given. So let's jump right in and see what this problem's about. Okay, this graph shows the fuel consumption, G, in miles per gallon, those are the units, of a car traveling at V miles per hour. Okay, so, depending on the speed a car is going, it's going to change the fuel consumption. May or may not be aware. And it's not a direct relationship, actually. So at one moment, the car was going 70 miles per hour, and its deceleration was 8,000 miles per hour squared. How fast was the fuel consumption changing at that moment? Okay, and then include units. So a bit to unpack here. I'll try to walk you through my thought process. So first of all, we got to figure out, what are we after? Question is asking for how fast was the fuel consumption changing? So fuel consumption, we know this is G. And when we see the words how fast, this is usually talking about a rate versus time. Okay. This is talking about, dt. And so what this is really telling us, I'll draw this down here. Or what are we after? We're after how fast G is changing with respect to time. In other words, we want dg dt. This is our end goal. Okay, if we've answered this, then we've answered the question. So what we have, though, is we have a graph of G and V. So this doesn't directly relate G to T. But we do have one other bit of information here in the prompt, was that at 70 miles per hour, so when V equals 70, the velocity of the car, its deceleration was 8,000 miles per hour squared. Now, 8,000, so we said deceleration, that's slowing down, so I'll say maybe that's negative 8,000 miles per hour squared. This is a rate, right, as we can see just by the units. Question is, what's this rate of? Well, deceleration is the rate that velocity is changing with respect to time. So this is really dv dt. Okay, you see how I'm kind of thinking of rates in this way based on kind of the units, the quantities in this ratio. Okay, so when v is 70, dv dt is this negative 8,000. So that's important because we want to know what the fuel consumption rate of change is at this moment when the speed is 70. So then we need something that relates dg dt and dv dt, because this is some information that I have already about the moment we're interested in. So one thing that would do that, and again, this would take some comfort with the idea as we've explored so far, is that dg dt is related to dv dt by the rate dg dv. Right? You could see how these dv's would cancel and we'd be left with dg dt on both sides. So this is the equation that relates the rates. Equation relating rates. Right? The rate that I have and the rate that I want. Right? I want dg dt. So at this moment, I know I have dv dt. That's given to us right here. I want dg dt. And so in order to do that, I must have no more unknowns in the equation. So I need to find dg dv. So how do I find dg dv? Well, this is a mouthful. Well, based on this graph, I have a graph relating G to V. What is dg dv in this context? Well, it would be the rate of change of G with respect to V, aka the slope of the tangent line. So we're looking for the slope of the tangent line at V equals 70. So it'd be right here. So one way we could do that is try to estimate a tangent line at this point based on the graph. And that's why I chose this problem, because I feel like a lot of students are not comfortable doing so. So here, again, I'm kind of making this up. It looks like I can get a pretty good tangent line if I go from here to here. I'll call this the tangent line T. And so since this has a grid, I can get a good idea for the slope. And the slope of the tangent line is going to be, you know, the rise over run here. So, you know, what we got, we dropped by, what, from 10 to, what is this, 20? Well, we'll just grab the slope because we don't need this point. So we dropped from 40 to 20 over a distance of, what, 70? So dg, dv is approximately, you know, 20 minus 40, change in the height over the change in the input. So that's negative 20 over 70, which is negative 2/7. So then dg dt is approximately negative 2/7 times dv dt we said was negative 8,000, all for a grand total of 2,300 miles per gallon. Oops. Should have paused here and had you guys think about this, but 2,300 miles per gallon per hour. You might be thinking, where the heck did you come up with that units, Mally? Well, miles per gallon per hour is going to be the units of dg dt. This is the units of fuel consumption over the units of time. Okay, so again, what made that problem challenging was figuring out what you needed by clearly reading the problem and understanding the units that you're after, taking all the given information, and then trying to find an equation that relates the rates, finding the missing information, and then solving the equation. Okay, so it is challenging in that way, but it's also formulaic in the sense that it will typically follow this type of strategy. Okay, so let's do another one. All right, for another example, we've got an airplane flying at 450 kilometers per hour at a constant altitude of 5 kilometers, and it's approaching a camera mounted on the ground. Okay, so theta is going to be the angle of elevation above the ground, and when theta is pi over 3 or 60 degrees, how fast does the camera have to rotate in order to keep the plane in view? Okay, so I'm going to try to kind of keep our approach similar so that you can sense a theme between the two. So looking at the end here, the question, how fast does the camera have to rotate? Okay, so the camera's at this point C. How fast, again, this is talking about dt, right? A rate with respect to time. And have to rotate, this is talking about the angle of rotation of the camera. You can assume this is kind of where it's pointing. So how fast is theta changing is what this is asking. So how do you represent the change of theta, instantaneous change in theta? That's d theta. Not loving this pen today. So then how fast does the camera have to rotate? We're looking for, we want d theta dt, right? This is what we're after at the end of the day. So we're on the hunt for an equation that will relate this thing that we don't have and want to information that we do have. So we know at the instant we care about that theta is pi over 3. And we have a rate here up top, some other information, that it's flying at 450 kilometers per hour in this direction. This altitude over here is fixed at 5. So we're going to name this distance between C and B, where the camera is, and this point under the plane. We're calling this X. So then this rate that was given, 450 kilometers per hour, is related to this distance X and the fact that it's shrinking this with respect to time. And so we know that for X, its change with respect to time is negative 450 kilometers per hour. Okay. So, and then this is fixed at 5 kilometers. I've got this distance shrinking, this rate that's given. So I know I'd like to use this because that is going to dictate how fast this changes. But I need something that relates d theta dt to dx dt. So really I'd love something that relates theta and x. And one thing that I have are the tools of trigonometry. And so, what relates x to theta? Well, this is the adjacent side to the angle. So we could see, there's a few ways to go about this, but probably the most efficient route would be to see that tangent of theta is opposite over adjacent 5 over x. And you're like, Mally, you said we'd relate d theta dt and dx dt. Yes, but we don't have those rates quite yet. So what we want to do is relate theta to x and then hopefully implicitly differentiate as functions of time and then get access to those rates in a new equation. Okay. So in other words, we will take this equation that relates now theta to x, right? And we will differentiate both sides with respect to time, as we've done before, assuming that that theta is a function of time, and that x is a function of time. Okay, I'm kind of thinking in quotes here. So that when we differentiate, right, we'll take the derivative of tangent theta, which is secant squared theta. But since we're differentiating with respect to time, and theta is implicitly a function of time, then we have to respect the chain rule, right? And so we'll get d theta dt out here, which is what we want, right? So this is good. And then on the right-hand side, this is really 5x to the minus 1. So when I differentiate with respect to time, I'll get negative 5x to the minus 2, but times dx dt, because again, x is an implicit function of time. All right. And so from here, it depends on what you want to do. You can input the rates that you know and then solve. So for example, we're looking for d theta dt, so we could divide both sides by secant squared theta, which is really like multiplying both sides, right? If secant squared theta is 1 over cos squared, then to cancel this out, we just multiply everything by cos squared theta, right? So we'll get here that negative 5x to the minus 2 times dx dt times cos squared of theta. And so we need to know everything on the right in order to figure out what the rate is on the left. So we've got most of what we need. We know that we've got theta is pi over 3. So this is really 5. I'm going to put this in open parentheses here because we don't know that. dx dt was negative 450, right? Cos squared of theta, we know that theta is pi over 3. So really the only thing that stands between us and knowing d theta dt is this value here of x. And so can we find this value of x at this moment? Well, yes. So let's do some side work here. When theta equals pi over 3, what do we know about this triangle? Well, okay, a little hiccup there in the recording. When theta is pi over 3, what do we know and how can we get to x? Well, we can't really use the Pythagorean theorem because we don't have all the sides figured out, right? And that would kind of be a pain to get. We can use the relationship between the angles and the sides, which are the trig functions. And so at theta equals pi over 3, at this moment, we know that we have actually some nice values here, that the cos of pi over 3 is 1/2. We know that the tangent of pi over 3 is radical 3. Okay. And so if you're looking for, x, which we said we had tan of theta is 5 over x, then we know that x is really 5 over tan theta, which is 5 over tangent of pi over 3, which is 5 over radical 3. Okay, so we've got this missing piece then here. This is 5 over radical 3. And, you can throw this all into your calculator or do it in pieces. That's fine. We know that, again, cos of pi over 3 is really a half. So squared, this would be a quarter over here. But what we'll end up with after all of that is 67.5. And again, what are the units? It's going to carry the units of d theta dt since all of our work was correct. Units of theta are in radians and time is in hours. Okay, so 67.5 radians per hour is the rate at which the camera needs to change. But, you can go ahead and convert this to radians per minute or per second just by doing some dimensional analysis, should the problem call for that. But the hardest part of this problem was what we just did. Identifying what you're after, relating the two rates together that you have by finding a new equation. Here it revolved around tangent of theta. And then going after the missing pieces that should be findable based on geometry, other formulas you have at your disposal based on the description of the problem to get that missing rate. All right.